Hello, and welcome to the first lecture in E&M. We're going to start with Chapter 21 on charges and fields, and we're going to break our lectures up into several parts. So this first part will be all about spherical charge distributions. So first of all, when we say that an object is charged, what do we really mean by this? Well, there's a couple things. If we have an electrical charge, we can assume that it has either extra electrons for negative charge or extra protons for positive charge. One thing to point out is that it's usually only the electrons that move, so positive charge is just an absence of electrons. One way that we know this is by thinking about the atom. The electrons are located in the outer parts of the atom. You can think of them as being in the electron clouds from quantum mechanics. And the protons are sort of stuck in the nucleus. They are attracted to each other and to neutrons through the nuclear strong force, which at the radius of the nucleus is much stronger than the electric force. So protons tend to stay put in the center of the atom. So a couple basics of fundamentals of electric charge. First of all, we call the charge on the electron negative E. And what that really means, and the charge on the proton, is plus E. This has a value of 1.602 times 10 to the negative 19th coulombs. So this is one of those cases where a unit was assigned to electrical charge, the coulomb, long before we knew what the size of the coulomb was. Contrast this with the kilogram, where people knew how much a kilogram was a long time ago. It turns out that in order to get a couple of coulombs, you need something about the size of a lightning bolt. So one difference between charge and mass is that a little bit of extra or excess charge has a very big effect. One thing to point out is that a charge Q is a multiple of the number of extra electrons or missing electrons. And we can use the equation Q is equal to NE. N would be therefore the number of excess or missing electrons. Okay, so the focus of this lesson is spherical distribution. So what do you think we mean by a spherical distribution law? One example is if you think about a planet. A planet is a spherical distribution of mass. And the distribution is such that we could write a density. The density is simply the amount of mass divided by the amount of volume. And we'll be talking about other distributions shortly. So to take this one step further, let's think about the surface area of a sphere. And we know that that surface area is 4 pi r squared, where we have a sphere with a radius of r. Now we're going to be doing a lot for surface area in this chapter, so it's important that you remember all of your areas. And we can talk about the spherical distribution law for gravity. So here it is, and if you took mechanics last semester, this would look familiar. This is the force of gravity is equal to big G, m1, m2, over r squared r hat. Now this r hat means that it is a radial force, which means that the force of gravity travels along a radius between two objects, for example. And we know this constant, capital G, is just the gravitational constant for the universe. And we know that m1 and m2 in this case have to be spherical or point masses. And one thing that you can show looking back at gravity is that a spherical object with a uniform distribution of mass behaves the same as a point object of the same mass. And that sound you hear in the background is my email, which I'll be sure to turn off for future videos. R in this is the separation between the centers of the masses. This is very important. It's a center to center distance. So if I have one planet and another planet, then I want R being the distance between the centers. And this is Newton's law of gravity. But there's a similar distribution law for electrical force. And this is Fe, the electrical force, equal to K Q1 Q2 over R squared. Again, this is in the R hat direction, so that makes it a vector. Now K in this case is a much larger constant, about 9 times 10 to the 9th. And Q1 and Q2 are either spherical or point charges. And again, you can show that outside of a spherical charge, Q1, that it behaves the same as a point charge, Q1. Now this is only true if you're looking at a point which is outside of that distribution. So for example, we didn't talk about what happens if we're located on the interior of a charge distribution. We're just talking about what happens if you're over here. But we'll get to that in a future video. And again, R is the separation between the centers, and we call this, one more fine point here, is that we typically rewrite this constant K as 1 over 4 pi times epsilon naught. And what that does for us is it allows us to write the force equation like so. And this is Coulomb's law, where we have Q1, Q2 over 4 pi R squared epsilon naught R hat. Now the reason that we want to write it like this is to take a look at this 4 pi R squared here. And you might recognize that this is the surface area of a sphere. And so both gravity and the electric force law are spherically symmetric. In other words, the force depends on 1 over the area. And you can see that if you look at this equation for F. And we'll come back to this a little bit later when we talk about Gauss's law. So how are these forces similar? They both follow spherical distribution laws, and as we said in the previous slide, F is proportional to 1 over the surface area of the sphere. How are they different? Well, electrical forces can be attractive or repulsive if you have two like charges, two pluses or two minuses, for example. This is, of course, repulsive. But if you have a positive and a negative, or a negative and a positive, then each of these cases would be attractive. Whereas gravitational forces are only attractive, and so there's the automatic negative sign in the force of gravity. There is a negative g m1 m2 over r squared, r hat. So directed inwards. In other words, if I have m1 and m2, the forces are directed towards each other. And gravitational forces are much weaker than electrical forces. If you take the ratio of the electric force between the proton and electron in the hydrogen atom and divide by the gravitational force, you get something around 10 to the 39th. So there's a huge difference in strength between the electric and gravitational force. And researchers are still thinking about why this occurs. One theory is that the force of gravity is actually leaking off into other dimensions than our familiar 3. And there's not a lot of evidence for this right now, but it is an interesting thought. Okay, so what if you have two charges? We said this in the previous slide. It's repulsive if we have the same sign and attractive if we have different signs. Now, because of Newton's third law, the force exerted by A on B as a vector is equal and opposite to the force exerted by B on A. And if you have more than two charges, then you need to use superposition. What you do is you determine the force on one charge due to the other charges in its vicinity, and you do vector addition. So you focus on one charge. And this charge says it's all about me. Who's nearby who can affect me? For example, let's write an expression for the force exerted on the upper right charge by the other two charges. The first thing we want to do is label them, so we can call this Q1 and Q2 and Q3. Next, we can draw the forces. So Q1, because it's negative, would be attracting Q2. So this would be the force of 1 on 2. And then charge Q3 would be repelling Q2 because they're both positive. So that would be the force of 3 on 2. Notice that what we're doing is we're isolating what would just happen to one charge. Next, we calculate the magnitudes of these forces. So F1 on 2 is going to be equal to K, Q1, Q2 over R12 squared. And this is the magnitude of that force. And so let's get out our calculators. And what you'll see here is that we have the symbol mu c. So mu, as a reminder, is times 10 to the minus 6. So that means that this force would be equal to 9 times 10 to the 9th. And let's not worry too much about its units right now. Q1 would be 2 times 10 to the minus 6 coulombs. Q2 would be 5 times 10 to the minus 6. And then the distance would simply be 0.10 meters, but that would have to be squared. So that's going to give us an electric force of 9, approximately. So the force of 1 on 2 is about 9 newtons. Now what's the direction? Using unit vectors, it's in the negative I-hat direction. And you can see that from the diagram. We do a similar calculation for the magnitude of the force of 3 on 2, and that's going to be equal to K Q3 Q2 over R32 squared. So R32 is the distance between 3 and 2. And when we do this, take a moment to plug it into your calculator. We get in the numerator 0.225, but now what do we use for the distance? Well, it's just 0.1 times the square root of 2, because it's the hypotenuse of a 45, 45, 90 triangle. So we chug that out, and we get that that's about 11.3 newtons, but that's at 45 degrees. Okay, so how do you break that up into components? Well, if it's at 45 degrees, then we can use sine and cosine of 45 degrees. And we get approximately, roughly 8 newtons in each direction. So it's roughly 8 newtons I hat plus 8 newtons j hat. Now at this point, what you may want to do when solving a homework problem is to set up your x and y directions, and this would be F1 on 2 and F3 on 2. and the x component of this would be negative 9 and 0, and this would be positive 8 and positive 8. And then adding up, we would get that the net force in the x direction would be negative 1, and in the y direction would be positive 8. This means that our F net in unit vector notation would be negative I hat plus 8 j hat, and that would all be in newtons. So feel free to pause if you need to work through this a little bit yourself. Next time, we'll talk about gravitational and electric fields. I hope that this was helpful, and we'll see you next time.